Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
Related rates is one of the places where I really start to enjoy calculus, and I like seeing how it gets applied to the real world. And one of these things that we have to think about is how one part of something that we do affects something else. So let's, for example, say you have some kind of building. Okay. And there was a ladder leaning up against it. Well, the ladder obviously is not going to change length, right? But as you pull the ladder away from the wall at a certain speed, right? So your speed would be in relation of time, the change in your horizontal with respect to time. The ladder itself would be falling downwards with respect to time. So at so many miles per hour. So the speed of one is going to affect the speed of the other. Okay, and one's going to have, in this case, positive velocity, and one's going to have negative velocity because one's getting longer and the other's falling down. So when it comes to these, here's what you're going to need. You're going to need a primary equation. Maybe a secondary equation. And that would be to help you reduce variables. But the most important thing that you need to know that you have to do is you need to do implicit differentiation. Okay, and what that is that dy dx. Now you're going to be doing dy dt and dx dt because everything's going to be with respect to time. And just know that yes, if you do dy dt divided by dx dt, that would be dy dt times dt over dx. Oh, yeah, that's dy over dx. Okay, so descriptive variables are definitely going to come up, and we're going to use that to our advantage. Okay, so here we go. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters a second. How fast is the radius increasing? And the diameter is 50 centimeters. Okay, so you've put air in a balloon before. So at first, like it starts that bubble and it gets really big really quick, but then as you go further out, like it doesn't seem to grow as fast. So the speed of which it's growing is changing, but the amount of air being put in is staying constant because we just have it hooked up to the same pump, 100 cubic centimeters per second, right? So the first thing we have to identify is a primary equation. We have a spherical balloon, and we're talking about volume, right? So here's that formula. Volume equals 4/3 pi r cubed. Okay, now we need to derive it. dv, technically dv dt, equals 4 pi r squared, and we derived r, so dr, technically dr dt. Okay, well, what is the rate of our volume? Because dv is change in, right? Change in volume per second is 100 centimeters cubed per second. What is our radius of our diameter? Is 50. That would be 25. And dr dt, well, that's what we're looking for. How fast is that radius changing? Okay, so we would have 100 over 100 pi would give us that answer. So we could say the radius is changing at, I forgot my squared. I knew something was wrong there. That'll change it. That'll make that 2,500. Okay. So 1 over 25 pi, or approximately 0.0127 centimeters per second. I don't know about you, but I don't know that I'm going to see less than half a centimeter each second. And so maybe we call that, as soon as it gets to that size, we're okay with it stopping, right? So 1, make sure you don't forget your squared. That'd be a big mistake on my part, right? And keep in mind, we're just touching base on this so we can see the beginnings. Like, there are uses, but obviously in math class, we just need you to learn how to solve it before you go out in the real world and apply it. We've already solved all these, so we know they're solvable. All right, so you have a 10-foot ladder leaning against a wall. The bottom is pulled away. At a rate of 1 foot per second. How fast is the top of the ladder sliding down the building if the ladder is 6 feet from the wall? Okay, so building ladder. That's all I know. Okay, I'm going to call this X and this Y. Notice I have not gone past this first statement. Is there any way I can relate those? Yes. X squared plus Y squared equals 10 squared. Okay, the bottom is pulled away at a rate of 1 foot per second. So that says dx dt equals 1. How fast is the top of the ladder sliding down? So dy dt is a question. And they tell us that we are 6 foot away from the wall. So they tell us x equals 6. Okay, what am I going to do? Well, I know I have to have my dx and my dy, so I'm going to come over here to x dx dt plus 2y dy dt equals 0. Now I'm going to substitute. 2 times x times dx plus 2 times y times dy dt equals, I don't have y. How can I substitute if I don't have y? That's kind of where that secondary equation comes in. We need to solve for y. Well, we can come back up here and go 6 squared plus y squared equals 10 squared, right? 100 minus 36 leaves us 64, so y must be 8. Okay, so now I can say 12 plus 16 dy dt equals 0. So I'll subtract 12, divide by 16. Negative 3/4, and that of course is going to be labeled the same. So it's going to be labeled in feet per second. Why is it negative? Because it's going down the wall. So try not to substitute anything that can change into your problem. If it can change, don't substitute it until after you've derived. Okay. You have a water tank that is in the shape of an inverted circular cone. What does that inverted circular cone look like? It looks like this. Please forgive my drawings. I'm not always the best at drawing. Okay, we would have a radius. We would have a height. Okay, so there's our cone. Water is being pumped in. Okay, so we have water pumping in. I'm not going to draw a faucet. You guys can get the idea there. At a rate of 2 cubic meters per minute. Okay. When full, the radius would equal 2 meters. And the height would equal 3 meters. Find the rate at which the water level is rising when the water is 2 meters deep. Okay. So we know that dV dt is 2 cubic meters per minute. Our goal is to find the water level rising, so that would be dH. We don't know anything about the radius and how fast the radius is changing, so we don't want the radius in our equation. So if you go back and you look for the volume of a cone, you will know that, by the way, anytime you have a 3D shape, it's always area of the base times the height. Because it comes to a point, we're multiplying by 1/3. But here's the deal, is we don't want the radius in here. We only know about dV, and we want to know dH. We don't want the radius in there. So we're going to have to do some kind of secondary equation to relate the radius and the height so that we can get rid of the radius in the formula. So let's compare the radius and the height. If there's no water in it, the radius and the height are both 0. If it's full, the radius is 2 and the height is 3, right? So if I did the slope, I'd get, look at it like this. This is the radius, this is the height. So 0, 0, 2, 3. So up 3 over 2. So the height equals 3 over 2 times the radius. But we don't want the height by itself, we want the radius by itself. So 2 over 3h equals r. Okay, so let's take care of that first. Volume equals 1/3 pi times 2/3 h squared h. So that would be 4/9, so 4/27 pi h cubed. Now we have something just based off volume and just based off height. We use that secondary equation to do some substitution. Now we can finally go ahead and move forward with our calculus. So dv dt equals 12 pi over 27 h squared dh dt, which is our goal, is to find that. Okay, well, we have the information. What are we going to do with it? Find the rate at which the water level is rising when the water is 2 meters deep. So the height is 2. So they tell us this is 2. And we know the water's coming in at 2 cubic meters per minute, right? So we should be able to solve. Two equals 112 pi over 27 times 2 squared dh dt. Okay. This really reduces, right? They divide by 3, so we have 4/9 pi times 4. So it'd be 16 over 9, or 16 pi over 9, right? Times by 9, 18 equals 16 pi dh dt. Divide by 18, or by 16 pi. That reduces to 9 over 8 pi. And that would be in meters per second, right? Because it was in meters per minute, not second. Okay, and we could get a decimal approximation. Nine divided by 8 pi. So approximately 0.36 meters per minute would be how much this thing is increasing. Okay. Why might we need to know this? Well, maybe you have a very, very big thing that you're filling up with water and you need to come back and when it hits full, so you need to know how long it's going to take to get full. Maybe you're running a computer program. Okay? Yes, I know computers can do a lot for us, but we have to program them first. All right, so let's look at another one. A little accident reconstruction might have to happen as well. And I know they have computer programs. Someone has to write the computer program. All right, we've got car A. Traveling west. $50 miles per hour. Car B is traveling north at 60 miles per hour. Both are headed towards the same intersection. at what rate are they approaching each other? When A is 3/10 of a mile and B is 4/10 of a mile from the intersection. Okay. Well, let's see here. Here's our two roads. A is traveling west at 50 miles per hour. B is traveling north at 60 miles per hour. So that would be where they're relating to each other, right? Now, notice that both of these are technically going to be negative speed because the distance between them is decreasing. This distance is decreasing, this distance is decreasing. It's not that their speed is negative, it's that their distance from the intersection is decreasing. So when I look at this part, we've got our x, we've got our y. X is getting smaller at negative 50 miles per hour because that's how fast it's getting smaller. Y is also getting smaller. Now we do know that we have a relationship here that x squared plus y squared equals c squared, right? And if I derive that, I would have 2x dx dt plus 2y dy dt equals 2c dc dt. And you might say, why is it okay to have 3 variables this time when last time you only had 2? Well, I'm looking for this rate right here. 60, not 50 right there. I know 2 rates. Last time they didn't tell me how fast the radius was changing. This time they told us how fast both cars were changing. All right, they did give us an x value, 0.3, and a y value of 0.4. So we could solve for c, or you guys know Pythagorean triples, there's the 3, 4, 5 triangle. So 0.3, 0.4, and 0.5. It's just scaled down. Or you could substitute into right here and find solve for c. So we want to solve how fast they're going to be coming at each other, right? Assuming neither of them put their brakes on. So 2 times x times dx dt plus 2 times y times dy dt equals 2 times c dc dt. Okay, well 2 times 0.5 is 1. So that's pretty easy to do, right? Two, 0.3, negative 50. 2.4, negative 60. Oops. Use those parentheses, right? Negative 78. And that would also be in miles per hour. So they're approaching each other at 78 miles per hour. Neither of them are going 78, but that would be the speed at which the impact would happen if they happen to impact right then. So one's 3/10 of a mile out, one's 4/10 of a mile out. They're half a mile away from each other, but they're approaching each other at a speed of 78 miles per hour. Okay, so that would play into a crash should it happen. So again, these are related rates. Okay, so here we have a man walking along a straight path at a speed of 4 feet per second. And the searchlight's on the ground 20 foot from the path and follows the man. At what rate is the searchlight rotating when the man is 15 feet from the point of the path closest to the searchlight? Okay, I think this one's kind of hard to think of initially. So I'm just going to give us, this is our searchlight. Okay, we'll do a brown line for the ground. Okay. And the searchlight is sitting on the ground, so we'll just give it a little dot right here. But we know that it's 20 feet from that path. Okay. Now it's going to stay here and it's going to rotate, so sometimes the light will be pointing this way, sometimes the light will be pointing this way. Then we've got a guy that's going to come along, and he's going to walk down the path. So as he walks closer, that angle is going to change, right? That's what we got going on here. So I'm going to draw my little guy here. So it looks like the light's up in the air. It's really not. It's on the ground. It's just shining at the guy. So keep in mind that this is not a 3D image drawn well. Everything except the guy is flat on the ground. The guy should be standing up off the page, but now, we know he's walking closer, right? And he's walking 4 feet per second. Okay, so he could be walking closer, he could be walking further away. We're not quite sure right now. So it depends on how you interpret this. We'll go with, but we do know he's walking 4 feet per second. And at first, we don't know this. Later, they ask us about the 15 feet. So let's just get a relationship between at what rate of speed. Well, the only way to relate these two is in a right triangle using tangent. So we're going to have to relate it to our angle. That's the only equation we can come up with. Tangent of theta is going to equal x over 20. Now the good news is, or we can rewrite this, tangent of theta equals 1/20th x. And we know dx dt is 4. But we need to know d theta. So we're going to have to derive this, but you may not remember how to derive tangent. So let's come over just real quick. We'll refresh our memory of what the derivative of tangent is. Y equals the tangent of x. Y equals sine of x over cosine of x. Now if I derive that using the quotient rule, low d high minus high, oops, positive cosine, d low all over the denominator squared. That gives us cosine squared plus sine squared, which is 1. 1 over cosine squared is the same as secant squared. So the derivative tangent is secant squared. Okay, so now that we have that refreshed, we can come in here, we can go, all right, secant squared theta d theta dt equals 1/20th dx dt. All right, they tell us dx dt is 4. We want to know this, but we don't know theta. Okay, so they give us x is 15 feet. So tangent of theta equals 1/20th times 15. So we're going to need to inverse tangent that, right? And I know I'm in radians, and that's fine. So I'm getting 0.643 So now we need to take that and the fact that x equals 15 and put them into this equation. So the secant of 0.643 squared times d theta dt is going to equal 1/20th dx dt, which is 4. All right, so secant is a reciprocal of cosine, right? So if I do cosine of that, we get 0.8. So if we do 1 over 0.8, we get 1.25. So we need 1.25 squared. It would be 4/20ths, which would be 1/5. So 1.5625 d theta dt equals 1/5, which is 0.2. 0.2 divided by that. So the rate that we're returning is about 0.128 radians per, what were you in? Feet per what? Second. So radians per second. Okay, so most of the time in trig or in calculus, you'll stay in radians if you can. We would prefer radians over. But the big idea is you're just going to have to stop and read each problem. And then you're going to have to pause and you're going to have to go, okay, what do I know is always there? What can stay in? Those numbers will stay the same. I was able to substitute 20 because that was always going to be 20. Then I could derive, and after I derive, then I can substitute things that vary. So make sure that you also are understanding what equation you're going to need. Are you going to need a trig equation, or are you going to need to use a Pythagorean relation? So be careful, draw a picture, and that way you understand whether things are moving closer or further apart. A picture will help every single time.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.